Bismillah ar-Rahman ar-Rahim. Good evening. Today we will try to do some summary to article related with manganite and the relation between the resistivity and temperature and many important and deep information like that. The article's names is Colossal electro resistance in this structure related with manganites and oxygen. Let's go to the next slide is the outline. We will talk about the abstract introduction, experimental details, and result conclusions, and at the last will be the reference. The reference will be the picture to this article about the author and the year published it, and some information related with this publishing and something like that. Let's start from abstract and let's take more information about the structure, what all of these elements, what all of these concentration, what does mean, what the condition related between all of these, which one is A, which one is B, like we said before. Here the structure is, the parent structure is AB, O3 or three atoms from oxygen related with all of these cations. Now at abstract, they note by direct current a closer. What does mean closer? Closer, that's mean here huge resistance, a drop, decrease around a metal, isolated metal transition, or temperature, we can say, because this is a critical transition point. After it, the material will convert from isolator to material, and we can say convert from ferromagnetic to magnetic. This structure is samarium 0.55. The author worked about on all of these concentration, on all of these two concentration, 0.55, and the second one will be 0.45. This condition, because all of these must equal 1, because the first one, like I said before, is samarium. It's a chemical element belong to rare earth family or group, and strontium here 0.45. Strontium is a one element belong to alkaline earth table, and like we know, here is the manganese, and the last one is the oxygen. Through solid state reaction method, the polycrystalline samples of this structure were synthesized. Now to another slide, they have been investigated by using X-ray diffraction. This is X-ray diffraction. We investigated 3 things by using this technique. These things is the scanning electron magnetism for grain morphology, and DC resistivity measurement techniques for the resistivity temperature behavior. The resistivity temperature behavior has been measured with different biasing currents. Here we will focus on this idea, all the articles, the most important things in this article. We will change the current, DC currents, from simple amounts, we will start from 1 milliampere until 50 milliampere, and we will note the difference about the resistivity, the electric resistance, and we will focus about the shape, the atoms, which one is in the top, what the difference in the top and the bottom, which one will be bigger than, and many important information like that. We will start from 1 milliampere, like I said before, and finished at 50 milliampere, and we will say what the change will be. Yes. With increasing the biasing, I mean the current from 1 milliampere to 50 milliampere, we will note interesting behavior, interesting phenomena. Let me explain what all of this. The resistance of the simples will decrease drastically. Will decrease. Why? The simples for bias current from 1 milliampere until 50 milliampere at a metal at an isolating metal transition until 50 milliampere, the resistivity will change to be approximately equal 250,000 60 from the ratio about 1 milliampere. This huge change, huge difference between these two numbers about the current. This phenomenon of electronic resistance is discussed about in this field, in this area. It is because we have a strong interaction between the ionic, between the spins, sorry. This spins corners is the carrier spins, and the second one is the oriented, or we can say the localized of this spins. That means we will focus about two things, and we will say these reasons to this strong interaction, or because this phenomena, because we have strong interaction between two corners of spins. The first one is the carrier spins, the second one is the localized spins. Because the strong interaction between the localized and the carrier spins, we note some interesting change when we change the current amount from 1 milliampere until 50 milliampere. In manganite ions and percolative mechanism of phase separation, this is very important. To another slide. Now, same structure, but with the original form. This rear earth with 1 minus x, and alkaline earth with x, both all of them equal 1. All of these elements act cations, and after that manganite oxygen. Rare earth and alkaline earth have interesting materials. We taking some important information about what and why all of these kinds of materials is very interesting to us, with their interesting properties like colossal magnetic resistance, charge ordering, electronic phase separation. All of these three sides have different qualities from the other, because that the rare earth and alkaline earth is a very interesting topic to us. By chemical composition, like strength of magnetic field, strength of electric field, temperature, pressure, can be do something like control point on the electric magnetic state of the manganites. Something like group has some elements will be the leader on the other, or control to relate something to field to go to another element. I try to explain the relation between these elements about the alkaline earth and rare earth with the manganites. They offer great opportunities for new electric devices, sure. In magneto-electronic and non-relative electronic, the disorder due to the ionic size mismatch. We will study what is the ionic size mismatch and how we can calculate it, and what the average and how we can benefit from shown column. The ionic size mismatch of rare earth and alkaline earth is another important factor to control the electronic phase of the doped magnet. The physical and electronic properties of the manganese depend on a few things. These things are the delicate balance of various delicate balance for a few things. First one, various electronic and the magnetic interactions. The last one be tainted by external disturbance, we can say. Yes, there is pronunciation to it. It's like that. Let me repeat that, it's important. The physical and electronic properties of the manganese depend on one thing. This is the dielectric delicate balance. But delicate balance to few things. These things are delicate balance of various electronic, delicate balance for magnetic interaction, delicate balance to tainted by external disturbance. That delicate balance is very important because the manganese depend on to select to determine the physical and the electronic properties. Let's take some examples like magnetic field, electric field, optical radiation. All of these due to the breaking of subtle balance between these interactions. We will know some balance, some breaking, some damage between these balance. I mean between these interactions, because that, like I said before, and we give some examples like magnetic field, electric field, and optical radiation. All of these phenomena or this action depend on the damage between the balance between the interactions. Here, the electric current, or we can say electric field, has a strong influence on electrical properties. Electrical properties take some actions or depend on important elements, as the electrical field has a strong influence on electrical properties. Some relation or important element about the electric field and the electrical properties. I'm talking about the manganese. And these can change the resistivity. Some relation between electric field has strong influence on the electrical properties, electric field, electrical properties. All of these relation or change can do change in the resistance to the manganese elements. Let's take some briefly or simply definition about what is the electric resistance. Is the change in electrical resistance with current. The short letters to it is ER, that means electronic resistance. Take the first letter from each word, from these two words, to be ER, is the change in electrical resistance with current. Electrical resistance was observed in thin film and single crystal manganese. Single crystal manganese and thin film was observed from all of these. The charge ordering will collapse, will damage, because the electric current the charge ordering, we can say, will disappear. Why? Because the electrical current. And like I said before, we will do some change, start from 1 milliampere until 15 milliampere. There is an isolating material transition or temperature melting of the colossal charge or ordering isolating state to ferromagnetic material state. This colossal electric resistance is dependent on this is important thing in this slide, because our topic was talking about the colossal electric resistance by using the specific structure. The colossal electric resistance is dependent on the microstructure of materials, the chemical constant, and the last one is the oxygen deficiency. The colossal electrical resistance is dependent on the microstructure of the material. Microstructure of the material is the first one. Second one is the chemical constituent, and the last one is the oxygen deficiency. Oxygen deficiency is the last dependent element in colossal electric resistance. Here, the magnetic compounds about this structure has interesting properties, especially in region 0.4 smaller than or equal 0.4 until bigger than or equal 0.4 and smaller than or equal 0.5 shows to us interesting properties between these two numbers inside this region. With similar Hall's doping concentration, what will be the large mismatch in the ionic radii of, we will note large mismatch in the ionic radii when in similar Hall's doping. In similar Hall doping, we will note a huge mismatch in the ionic radii of the SM3 plus and SR cerium 2 plus from 1.13 angstrom to 1.31 angstrom. This is a huge difference, give increase in the A cations disorder in the structure. It shows interesting properties to the electronic phonon magnetic properties as compared to other manganites. Like I said before, we have if I using the parent compound ABMN oxygen, free oxygen. When we do comparison between the A properties with the MN, we will see interesting things in the electronic photon magnetic fields. Now we'll use this equation to calculate the mismatch. Here, a summation, Xi is the fractional occupancies, Ri is ionic radii of respective A cation size. All of these two elements, we can find the right results about it from shown radii from Google. And here the average ionic radius, we can calculate it by using this equation, summation n until I xi dot ri divided on n. And the mismatch will be 7.8 dot 10 to force minus 3 angstrom for this structure. Introduction, let's keep going in introduction. A large disorder will decrease the electronic correlation length. The composition with X equal 0.45 here is important. Shows what? Shows a sharp change in 2 or 3 regions. Electrical resistivity, coefficient of volume expansion, volume magnet obstruction near from the core temperature. At the X equal 0.45, we will, no angstrom, sure, we will see a sharp change in 3 fields: electrical resistivity, coefficient of volume, and volume magnet obstruction near from core temperature. Here, let's start from experimental details by using the same form. We're talking about using solid state reaction method. The expected chemical reaction will be like that. Calcinations were done at 950 Celsius for 24 hours to 1 day. The billets were sintered at 1,200 Celsius and 103,000 Celsius for 1 day, each with intermediate grindings to ensure that chemical reaction goes to completion and to end, and that the material product contains only the desired homogeneous single phase. This is very important to be sure all this contains will go directly to be homogeneous single phase. Homogeneous single phase starts from 950 Celsius to 1 day, and after that increase the temperature. The bells were centered at these 2 specific temperature degrees, 1,200 Celsius and 1,300 Celsius to 1 day. In order to reduce the Joule heating, the resistivity measurement was done in a plus mode, where the direct current was applied only for a few milliseconds, and voltage was measured at the instant. At the instant, just only measure few milliseconds and few millivoltage at this instant. Resistivity measurements were performed by this equation, the length dot breadth dot thickness to be like that. Here is important image, and another one will be to the important by understanding what that's all of these images meaning. We can do some imagination idea in our mind to can think what this process is be. The positional parameters and cations occupancy are refined while keeping the oxygen content fixed. We must focus on the oxygen while keeping the oxygen content fixed. All the reflection lines here, like we see in this figure, in this image, X-ray source give us the X-ray beams, and after that, the samples. We use this way to can calculate the distance between every 2 atoms, and to illustrate and study the important characteristics related with this sample by using this way. X-ray source give to us the X-ray beams, and after that diffracted X-ray. Here this detector will be something like screen to show to us the results, and after that we can note what is the change, what's the important things, and something like that. And after that we will focus on the Bragg's law. This will be very important to calculate the theta or the distance between these two atoms or the wavelength, okay, by focus on using the Bragg's law. All the reflections lines were successfully indexed according to an orthorhombic perovskite structure with this process PENMA or PNMA space group. It's very important. All of these squares are atoms. And after that, let's take a look what this screen will show to us. Will be something like that, sharp increasing in some critical points to be like that. With this image illustrate to us the relation between the angles and the intensity. And like we seen here, we have increasing, sharp increasing in some critical points like that. Like I said before here, because this sharp increasing, that's mean here we're dealing with polycrystalline elements, with single crystal element. When we're dealing with polycrystalline element, the sharp increasing will be like that, with some distance between these 2 points. Well, this distance will be bigger. That's mean we're dealing with polycrystalline material, but here we're dealing with single crystalline materials, because that we noted the sharp increasing in this critical points. The disorder parameter here equal, like I said before, which is bigger than of lanthanum, bigger than praseodymium, bigger than neodymium, based manganese of similar composition. Disordering in the cation size strongly influences the degree of electron lattice coupling. The disorder in the cation size strongly influences the degree of electron lattice coupling. Influence have some directly effects on the degrees of electron lattice coupling. Now let's see what will increase, what will decrease. Larger values of the mismatch, square mismatch, what will lead to an increase in scatter in the electron hopping integral for neighboring manganite sites at fixed values. Large mismatch square value will act to increase the scatter in the electronic hopping integral for neighboring manganite sites at specific values, sure. Now, of the manganite valence and the radius, like I said before, we can find these results from the shown column. An increase in mismatch cases a weakening, an increase in mismatch, what will do? Well, cases a weakening of the ferromagnetic and intrinsic ferromagnetic interaction and destabilization of the charge order. The most important things here, large mismatch will cases a weakening of the ferromagnetic interactions, weakening in the ferromagnetic interaction when we dealing with increasing in the mismatch. Here, this image illustrates to us the shape of this simple. Here, this balls, and the bottom, the top, what the difference, what that's mean. A fractured surface was used to see the grain microstructure within the pellets, which provides a better view of the grains. a better view of the grains development and grain sizes than that of the morphologists of the top or the bottom surface of the pellets. Here, the scanning electron magnetism image of a fractured surface of this sample. Here it is clear that grains have well-defined spherical morphology and have sizes of the order of 1 micrometer. Have sizes of the order of 1 micrometer. This spherical morphology showed to us. These grains are homogeneously distributed, homogeneously distributed, is important, throughout the bulk of the sample. Throughout the bulk of the system, these grains will show to us the homogeneously distributed. When the bulk out of the sample. It's important, this word, because shows to us the shape of these bells through the bulk of the sample, because that I use the picture again. Here, this figure number 3, related between the temperature and the resistivity. The resistivity temperature plot of the sample with different measurement applied current. Here, like I said before, this is the most important slides at all the this presentation, because the critical point, it's here. Like I said before, we will change the amount of current, start from 1 milliampere until 50 milliampere. We will say something at 1 milliampere, our curve will be like that. We'll target higher target with the resistivity approximately 350 ohm centimeter. And when we increase the temperature to be 2.5, the resistivity will decrease at the top point will be something like 220. That's huge decreasing. And keep going, we will say the same thing. When I increase the current, the resistivity will decrease. It's an interesting phenomenon to us, to any physicist in this field. Now, it shows that the resistivity in the vicinity of the isolating material temperature decrease with increase applied current, like I said before. But here, let's focus at for 50 milliampere current, the resistivity dropped drastically at isolating material temperature. Let's take another picture. Here we're talking about that at 15 milliampere. It's dropped to be approximately like or equal the isolating material temperature. Let's say I'm wondering, where is the isolating material temperature in all of these 5 curves? Will be here. We can take a line, draw a line from the top point until the t-axis, and after that can calculate the isolating material temperature and this critical temperature. Why? Because until this temperature at this field, the material is isolating, and at the same time we can say it is paramagnetic. After cross this temperature, the material will start to act like a magnetic, to be like a material. The resistivity drop is over 2 orders of manganite to compression to resistivity for 1 milliampere current. Like I said before, this is very important. And here, the resistivity drop is over 2 orders of manganite in comparison to resistivity of 1 milliampere. It's a huge difference between these two cases when 1 milliampere and until 50 milliampere, like we said before. The first one at 1 milliampere. The last one will be start to act to be approximately equal the isolating temperature, isolating metal temperature will be equal this point here, equal approximately 185. All the curve be near from this point. Here is a huge difference. Here is the critical point. Now, like I said before, the electronic resistance, we have two kinds of, or we can define the electronic resistance by using two ways, absolute and relative electric resistance. Let's take simple information about absolute electronic resistance can be calculated from current voltage characteristics. The equation here, 100 dot resistivity to I number 1 minus resistivity I number 2 between two brackets divided on resistivity I number 2. Here resistivity I number 1 is the resistivities of the current number 1, and here to current number 2. It's important to can calculate the absolute electronic resistance. And here, the last figure with us will be something like the current number 1 will be constant, and we will just change the current number 2 from 2.5 milliampere until 50 milliampere. Let me repeat that. Started from 2.5 milliampere until 50 milliampere, and we will say what the difference are. Here, this figure 4 describes the T dependence of relative electronic resistance for constant current number 1 milliampere, and with different amount of current number 2. Electronic resistance is maximum at the isolating material temperature. Here, this image illustrates to us the relation between temperature and electronic resistance, not resistivity, but here with electronic resistivity. Because that, like I said before, the maximum electronic resistivity amount value will equal the isolating material temperature, like we see here. This at I equal 50 milliampere. Here, when I2 equal 10 milliampere. Let's note something. When it starts from 2.5 milliampere, the resistivity here approximately 125. And when increasing the temperature, the resistivity increasing too. And like I said before, the maximum electronic resistivity will equal isolating temperature, isolating metal temperature. That's mean here when increasing the current, the electronic resistivity to increasing. I think it's the last slide, the last one, with all of these amounts of current number 2, the resistivity, electronic resistivity equal all of these amounts, respectively at isolating material temperature, although heating can have some influence on the value of the resistivity. At the highest biased current, high temperature can do some influence on the resistivity. The measurement is done in a plus mode of few milliseconds, the sample couldn't be heated much to affect its resistivity. Therefore, the simple Joule heating can't account for the observed gained electronic resistivity, considering such a large change in resistivity. This the conclusions and something like summary to all I said it before, like the difference between 1 milliampere to 50 milliampere, the ratio equal approximately 250-16 100%. It's a huge and interesting amount to any physicist. And the original of this phenomena is due to the strong interaction between the spins, the localized spins and the carrier spins, the interaction between these carrier spins and localized spins. This is huge because this strong interaction between these corners of spins. This work can be useful for the potential application of the electric resistance, such a non-invariant memory element. I think that's it. Thank you about your watching, your listening. I hope it was helpful to us. Have a good day. See you in the next lecture.